Hello, everybody. I'm very excited about this video. For the first time really in this semester, we are going to take a look at the universe in a different wavelength of light. We're going to look at the fascinating field of radio astronomy, our other spectral window. The light that can come through the atmosphere and reach the Earth happens to be mostly radio wave light, so we can build radio telescopes here on the ground and take a look at what the universe looks like in radio wave light. So let's talk about radio astronomy and radio telescopes. And I'm going to go through a presentation, and then I want to show you the current state of some radio astronomy. We're seeing a little bit of it right here. What we're looking at right here is a galaxy. The galaxy Centaurus A is the fifth brightest galaxy in the night sky. You can't see it with the naked eye, though. And what we're looking at is this galaxy in three different wavelengths of light, one of which is radio. So we have our two spectral windows, the type of the light from the electromagnetic spectrum that can actually go through the atmosphere and reach the surface of the Earth, visible light, sometimes called optical light, and radio wave light. And that's two pieces of this image. So you can take a picture of this galaxy, Centaurus A, in visible light with, say, the Hubble Space Telescope, and it looks like this. You could use a radio telescope, say the Very Large Array in New Mexico. You get a picture that looks like this. And you could also take an X-ray photo, say using the Chandra X-ray Observatory, and this galaxy would look like this up here. Clearly, looking at the universe in different wavelengths gives us incredibly different information. This is why we want to study the universe in all possible wavelengths. This top image, the X-ray image, requires a space telescope, but these two are done with can be done with ground-based telescopes. Sure, the optical images with the Hubble Space Telescope, but that's because it's awesome. But you could get a comparable image with ground-based telescopes. And let's take a look right here. This looks like a space picture of a galaxy. Sure, it's a kind of a weird looking galaxy, but that's kind of what I expect if you're going to show me a picture of a galaxy. If you just showed me this picture and said, hey, that's a galaxy, I might be, since I've been trained as an astronomer, like, oh yeah, that's a radio galaxy. Awesome, cool. But you, looking at this for the first time ever, be like, that's not what galaxies look like. What you're seeing here in the radio wave light is a completely different set of information. You're seeing what are called radio jets. And that makes this type of galaxy a radio galaxy because it has these jets that scream out for hundreds of thousands of light years out of the poles of the galaxy. These radio jets are powered by the supermassive black hole at the core, at the center of this galaxy. So we can see these radio jets, which are absolutely enormous. And we can use this information not only to study the production of radio waves in galaxies and get a more full view of what this galaxy looks like, but as a way to actually get information about the supermassive black hole at the cores of all large galaxies. And then we could go through a similar game, but this is not a video about X-ray astronomy. This is a video about radio astronomy. And radio or X-ray astronomy is offering a whole new set. And you can see each part complements the other one. And by putting all the pieces of the electromagnetic spectrum together, we get a more full view of what's going on. So that's what they do in this central image, is they just overlay all three images on top of one another in a so-called composite image. And now you can study the structure, the radio galaxies, and the X-ray part all together simultaneously. Okay, so let's actually talk about radio astronomy. If you remember from the previous video or from going through the notes, and I always assume you've gone through the notes, you will remember that we have two spectral windows. These are the places where our atmosphere is transparent to a certain part of the electromagnetic spectrum. That means our atmosphere is basically a window. The light can come from outer space and go through our atmosphere no problem to reach us here at the ground, where we can build telescopes to study that light and to study those celestial objects. Our two spectral windows, the big ones were visible light, represented by the rainbow right here, and then radio waves as well. So if we build visible light optical telescopes, which is what we've talked about this entire time from on the ground, why can't we build radio telescopes? So why don't we just build a radio telescope that operates in this spectral window and study the radio universe? So because we have these two spectral windows, we can do what we call ground-based astronomy, astronomy that can be done from the surface of the Earth, where we don't have to really worry too much about the atmosphere. And we can do visible light astronomy from the ground and radio wave light astronomy, which gives us an entire sub branch of astronomy called radio astronomy, which is absolutely fascinating. It gives us an entire new view of the universe, what the universe would look like if we had radio eyes instead of visible light eyes, eyes that detected radio waves instead of visible light. We can see all the stuff related to what produces radio waves and interacts with the radio waves. We can see the radio universe. And that field is called radio astronomy. But to do it, we need radio telescopes. So, how do we build a radio wave telescope? I mean, we communicate with radio waves all the time. Anytime you tune into the radio or use your cell phone, you're communicating via radio waves. Radio waves clearly go through things like glass and buildings and pretty much everything. Well, not everything, but they go through a lot of things. And that's why it's such a useful wavelength range for communication. So, how would we build a telescope that has a mirror for radio waves? If radio waves go right through glass, all the telescopes that we've built so far are useless because the radio waves go straight through the primary mirror. Clearly, we need a different kind of telescope. And what we're going to do is we're going to build a reflecting telescope where our mirror will become a metal dish. Metal is extraordinarily good at reflecting radio waves. So instead of building a glass mirror to reflect visible light waves, we want to build a metal dish to reflect radio waves. If you've ever seen somebody with a satellite dish on the side of their house, many of you probably grew up with one, you actually had a mini radio telescope on the side of your house. Because a radio telescope is essentially a giant metal dish, so light can come in, radio wave light can reflect off the metal dish. And we don't use a secondary mirror because these radio dishes can be pretty big. We just let the light come to focus pretty much at a detector. So we actually call these prime focus reflecting telescopes. Something that you don't need to know. No secondary mirror, but it makes all radio telescopes look like this. This is the Green Bank Telescope in West Virginia. And clearly this diagram was based off of this telescope. This is the largest single dish steerable where they can point it anywhere in the sky radio telescope. So we're going to use we're going to use metal dishes to reflect radio waves, which means that, hey, we can make radio telescopes really, 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 really big because we can form a very large metal dish and it won't deform underneath its own weight. Okay, so now we have our radio telescopes. They are reflecting telescopes of a slightly different design, and they use metal dishes to reflect radio waves instead of glass mirrors. Radio astronomy is the study of the universe at radio wavelengths. Radio wavelengths are pretty much any wavelength that's about a millimeter in wavelength and larger. So that's the boundary, the rough boundary between microwave and radio. Now we can get some microwaves just a little bit less than a millimeter wavelengths do make it to the surface of the Earth. So we can do some microwave astronomy, and that's right at the boundary of radio and microwave. Okay, so let's talk a little bit about what we're going to be doing with the radio astronomy. Radio waves have very long wavelengths. That means they have very low energy because the energy of a photon is inversely proportional to the wavelength of light. So a very long wavelength, it translates to a very low energy photon. So the lower energy radiation means that we're going to be studying the colder parts of the universe, the things that give off preferentially radio wave light. And remember that there's this connection via Wien's law to the types of light that objects prefer to give off and temperature. Colder objects like to give off preferentially shorter or longer wavelengths. But this also is going to include some of the most energetic phenomena in the world, which can also produce radio waves, like those radio jets out of that galaxy that are being produced by things that are related to the supermassive black hole at the core of the galaxy. Radio astronomy, if you remember when we talked about the molecular lines for molecules, we could rotate molecules, and we could rotate molecules at different speeds. There was an entire suite of rotational molecular lines. And these were all in the radio part of the electromagnetic spectrum. So radio astronomy allows us to study the molecular universe. What molecules are forming out there in outer space? Where are the molecules? And also radio waves, since they clearly go through like the air in this room, the brick walls that I have here in my place, the windows here, clouds in the sky, rain, dust storms, whatever. Radio telescopes can operate 24 hours. They don't care about the sun. The sun's pretty quiet in radio waves. So yes, this telescope is probably operating here in the middle of the day. Even if it was cloudy, it can still operate because radio waves travel easily through pretty much everything out there. We had to build a metal dish just to harness them and to focus the radio waves, which not only does that allow radio telescopes operate 24/7, but it also gives us a view of through the dust in the universe. So many very, very interesting parts of the universe, like where stars are forming, where planetary systems are forming. The cores of galaxies are enshrouded by giant clouds of gas and dust. The dust blocks all the visible light that's leaving those regions from ever reaching us. We can't see them in visible light. Radio waves will go straight through that dust. So radio astronomy is going to give us a way to peer through the dust of the universe and get behind the enshrouding veils that all of these objects have. So we can look through the dust to see what's happening for, say, star formation or planetary system formation. So radio astronomy is deeply, deeply fascinating and a huge field of astronomy. So this is just the same information, just a little bit consolidated right here. Well, I wanted to go ahead and show you another radio galaxy. So this radio galaxy is called Hercules A. And here, this is not a spiral galaxy. This is an elliptical galaxy right here. And you can see that's the visible light, the sort of off-white, egg white color. There's our elliptical galaxy. And here's two giant radio jets. So here we're combining visible light from the Hubble Space Telescope and radio wave light from the VLA radio telescope, the VLA, the Very Large Array. And this is just the same things that I just mentioned on the previous slide. So let's go ahead and take a look at how radio astronomy operates. And we talked about all the amazing benefits, but there is a huge, huge problem with trying to do radio astronomy. And that is that just by the nature of we're studying the universe in radio waves, our angular resolution for any telescope we design is going to be pretty poor. It's going to be really, really bad. So radio astronomy suffers from bad angular resolution unless we can come up with a clever way to get around that. Why is that? Well, that's weird. Those weren't supposed to come in that order. But why is that? Why do we have this major problem in radio astronomy that radio telescopes suffer from inherently bad, very large values of angular resolution? Remember, a large value of angular resolution means two things can be separated by an enormous angular distance, and they'll still get blurred together into a single blob. So we want angular resolution to be a very, very small number. That's good angular resolution. And if we just look at how we figure out angular resolution, we can see this problem with radio wave astronomy very, very quickly. So remember, the angular resolution is proportional to the wavelength of light that we're studying, and now we're studying radio waves, divided by the diameter of the telescope. Radio waves are the longest wavelength radiation of the electromagnetic spectrum. Your typical radio wave that we are going to be studying with a telescope has wavelengths of 100,000 to 1,000,000 times longer than visible light wavelengths. 100,000 to 1,000,000 times longer wavelengths. So if I were to plug in a number that's 100,000 to 1,000,000 times larger up here, I'd end up with an angular resolution that's 100,000 to 1,000,000 times larger for the same diameter telescope. So for the same size telescope, a radio telescope will have an angular resolution that's 100,000 to 1,000,000 times worse than a visible light telescope. That's really, really blurry. How can we get around this? Well, We can play with the denominator part. The angular resolution is inversely proportional to the diameter of the telescope. A good thing we can now work with metal dishes because we can make ridiculously large metal dishes. This right here is the largest radio telescope in the world. It's located in China. It's called the FAST telescope, and it's the largest single dish radio telescope. So from one edge to the other edge of this big dish that basically just sits in the bowl of a mountain is 500 meters, half a kilometer. So that is a huge, huge half a kilometer radio dish. However, just because you have to focus the light, you can only effectively use about 300 meters of observing diameter at any time. And you bounce the light to one of these 3 radio towers right here, so you can detect whatever you are looking at. That's where the light is focusing. So it has an effective observing diameter of 300 meters. Notice that our largest visible light telescopes are currently on the order of 10 meters in size. So this is 30 times larger than our biggest visible light telescopes. But even with such a huge diameter, this radio telescope primarily operates at about 10 centimeter wavelengths, that part of the radio spectrum, wavelengths of 10 centimeters. So I can calculate the angular resolution of the biggest radio telescope in the world by using my angular resolution formula, things that you don't have to do for this class, but I'll crunch the numbers, is this equation right here. You get my angular resolution in arc seconds, and I get 83.3 arc seconds. That's more than 1 arc minute. Remember, an arc minute is 60 arc seconds. This largest radio telescope in the world has worse angular resolution than your eye. This telescope sees a blurrier sky than your eye does at radio wavelengths. The biggest telescope in the world. And here, a visible light telescope, our eyeball, with a diameter of just a couple of millimeters, sees more detail in the universe than this giant telescope can. Radio waves to make it so radio astronomy have terrible angular resolution, even for our largest telescopes. So just going through the math right there, we would really like to look at the radio universe with a high level of detail, right? We want to be able to see the smaller bits. We want to see what the radio universe looks like in high detail. How can we get around this major problem of long wavelengths of radio waves, mean that radio astronomy, for a single dish, even the largest single dish, still has terrible angular resolution? We can rely on the fact that humans are clever, and we can build technology that gets us around. Let's see here. Sorry about that. I thought I had animated this slide. We can use technology to get around the bad angular resolution of radio astronomy. And how do we do this? We improve the angular resolution by building what we call interferometers. That's an interference meter. Interferometer. And this is a type of technology that's going to take advantage of another wave property of light, interference, something we haven't really talked about in this class. Basically, that says picture water waves, so waves on the surface of a pool, or waves on an ocean, or waves on a lake. And if you have 2 wave crests that coincide with one another, those 2 waves will add together. They constructively interfere to make a bigger wave. But if you had a wave crest meet a wave trough, and those 2 waves ran into each other where the crest, one's at a crest and the other's at the trough, they'll cancel each other out. They'll interfere and destructively interfere to cancel each other out. So how waves actually meet up with one another in what's called phase space, complicated stuff, but that's why I'm not going to go over it in detail in this class. But how waves interact with one another, interfere with one another, gives us an entire new wave property that we can play around with. And it allows us to create some pretty clever technologies where we can we can take advantage of the interference of light. How do we do that? We build these large arrays of telescopes where we can see all the different ways that light waves could interfere as they land, say, on this telescope versus this telescope. So we build a large array of radio telescopes and then link them together with a computer so we can simultaneously see and process what each telescope is observing simultaneously. So we build arrays of telescopes that are linked together by a computer, and by doing that linking together and taking advantage of this interference wave property of light, we can create one giant super telescope that we call an interferometer. What is the benefit of this? By linking them together, you basically are increasing the effective diameter, where every telescope in the interferometer becomes a part of this giant super telescope. And the diameter of this giant super telescope that we call an interferometer is the largest distance between any of the telescopes in there. So you find one telescope, you go to the farthest telescope away. If that's the largest distance between any two telescopes in the interferometer, that's the diameter, the effective diameter of an interferometer. So now we can widely space telescopes to get a larger effective diameter. And notice that if we can increase the diameter, we can decrease the angular resolution. And I know this is a little bit confusing. Just go with that we have the technology where we can link telescopes together to act as one super telescope. And these arrays of linked telescopes are what we call radio interferometers if we're operating in the radio part of the spectrum. We could make microwave interferometers, infrared interferometers, and we could even make, there's one visible light interferometer in operation right now. The longer the wavelength, the easier it is to construct these, the easier it is to get the computers to process the data simultaneously, the easier it is to engineer and have the positioning of the telescopes be right. So most interferometers are radio interferometers. One of the most famous radio interferometers is in Socorro, New Mexico. It's called the Very Large Array. If you've ever seen the movie Contact, you've seen the VLA. And it is composed of 27 different telescopes. That each telescope that you're seeing here is 25 meters in diameter. So let's look at how these actually work. How do these radio or microwave or even infrared interferometers work? How do interferometers work? And remember that we're linking them together to get a better angular resolution. And we're going to create a effective diameter, which is going to be equal to the farthest distance between any of the two telescopes in the array. That will determine our effective diameter. And I'm going to show you this with a graphic on the next slide. But I want to go ahead and show you how this works at increasing angular resolution first with some real examples. So let's take the example of the VLA. This is not all 27 dishes. This is only a subset. They're laid out in this nice pattern that is kind of like a giant triangle, where you can go out this way and you can go out this way and you can go out this way. There are little railroad tracks so you can reposition the telescopes. At the widest positioning, the largest distance between any two telescopes would be from this telescope all the way out to the end branch of this one, this line of telescopes. So at its widest configuration, the VLA has two telescopes that are positioned 30 kilometers away from one another. 30 kilometers. That's 30,000 meters. And since that's the largest distance between any of the two telescopes in the interferometer, that becomes the effective diameter of that telescope working together, that interferometer working together as a super telescope. Now that was a lot of words, but really what that boils down to, it means that whenever we calculate angular resolution, we get to put 30 kilometers here. I want to demonstrate that with the world's currently most advanced interferometer. It's in the Atacama Desert in the deserts of Chile. It's called the Atacama Large Millimeter Array because it operates at about a millimeter or so. right at the radio microwave boundary. So Atacama Large Millimeter Array, this is called ALMA, and it's 66 12-meter telescopes. And you can rearrange the configuration. You can make it really compact where they're all, the largest distance between any of the two telescopes is about 150 meters, or you can spread it way out so that the largest distance between any two telescopes is about 15 meters. Let's take that, or 15 kilometers, sorry, 15 kilometers. Let's take that largest separation between the telescopes, that wide arrangement of these telescopes. That will give us a effective diameter of 15 kilometers, 15,000 meters. And now let's calculate the angular resolution that all of these telescopes in an array working together, working as an interferometer, a super telescope. What kind of angular resolution can this interferometer get? All right, so it's operating, it's the large millimeter array. It is most sensitive. It primarily operates at 1 millimeter wavelengths. That's 1,000 micrometers. So I can go ahead and put this into my angular resolution equation. What's the wavelength? 1,000 microns. What is the effective diameter? 15 kilometers, 15,000 meters. Crunch those numbers, and I get an angular resolution of 0.0167 arc seconds. That's about 4 times better, 4 times smaller than the Hubble Space Telescope. Gone are the days of low resolution radio astronomy and microwave astronomy. We have overcome the biggest disadvantage of radio astronomy, the fact that radio waves have long wavelengths and therefore it's very difficult to get good angular resolution. We use a technological solution. We built interferometers linking telescopes together to create a super telescope. And now we have radio wavelengths that we can build on the ground, the surface of the Earth, that are getting better angular resolution than Hubble, which is operating at diffraction limited resolution. That's incredible. That's absolutely incredible. Now, since this effective diameter thing is a little bit confusing, I wanted to come up with my own fake interferometer. So here's my best work as an artist to create my own imaginary interferometer. So let's see here. How many telescopes did I put in this? This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 telescopes in this in my interferometer, and they're in an arrangement like so. So what I want to do is I want to demonstrate to you that the effective diameter of an interferometer, whenever we're going to calculate the angular resolution, the effective diameter is what we want, and it's going to be the longest distance between any two of the linked telescopes. So let's go ahead and have a look at this. So here's my interferometer. Each one of these radio telescopes is a 25-meter radio telescope. Just picked a number. They're spaced out. So on average, the average distance between any of the two telescopes is about 1 kilometer. But all of that information, while it is important to the actual operations of an interferometer, what we're after here, the effective diameter, is determined by the longest distance you can find between two telescopes. And that would be this right here. And this would end up being 6 kilometers between this telescope and this telescope. So this interferometer has an effective diameter of 6 kilometers. So you always want to look at the largest distance between two telescopes of the array, and that sets the effective diameter. If you've seen those images of the black hole that we got about a year ago, 2 years ago, a year ago, 2 years ago, I don't know time anymore, but absolutely stunning image. They use what they call the Event Horizon Telescope, which is using radio telescopes distributed all over the surface of the Earth that they've linked together. So they're using a interferometer, a radio interferometer that has an effective diameter of the size of the Earth to get that image of a black hole. And that linked system is called the Event Horizon Telescope. And now that's the core of the material I really wanted to cover for radio astronomy. Now I want to share with you just some of the amazing work that we can do now that we have these interferometers, which those are relatively new, past 50-ish years or so. And now that we have really high resolution interferometers like the ALMA array that are pushing resolutions in radio and microwave wavelengths to be comparable to or better than Hubble, we can get some pretty amazing detailed images that combine radio wave light, microwave light, and visible light. So right here, we're just looking at two galaxies that are actually colliding with one another. So these are two interacting galaxies. They're NGC 4038 and 4039. This galaxy is colliding with this galaxy, and they're going to slowly merge together. A pretty awesome natural phenomenon that I certainly would like to know more about. This is what it looks like in visible light. You can see there's some vigorous star formation. See all this red light right here? A nice wavelength of 656.3 nanometers. You're seeing hot hydrogen gas glowing right there. And you can see all the dust here as well. As these two galaxies merge, this is what it looks like in visible light. This is what it looks like in radio wave light. That's showing us where basically all the molecules are and where our supermassive black holes are. So here's the core of this galaxy, here's the core of that galaxy. Pretty bright in radio here, pretty bright in radio there. And then we can take these images and build these composite images to build an image that looks like this. And now we can leverage two parts of the electromagnetic spectrum to learn a lot about these two galaxies that are colliding and how galaxies collide and eventually merge. And we think that the history of galaxies in the universe is just a series of galaxies merging, interacting by merging, coming together and building larger and larger galaxies. This is just a really cool image. This is looking at the Orion cloud. So if you look at the constellation of Orion, you'll see that it's basically behind Orion, not all the stars because they're spread out all over space. But in the direction of Orion, there's this huge molecular cloud complex, clouds made of molecules in space. And this is looking at one part of this huge Orion molecular cloud complex. So here's the molecular cloud complex. This background image right here is taken with the Gemini, is a visible light image, I believe. No, it's a radio. It is all radio image with ALMA. And what it's highlighting right here is it's pinpointing all of these yellow circles are indicating where we have detected and confirmed new stars are being born, individual stars being born out of this giant complex of gas and dust, these molecular clouds. Not only that, you think, wow, we can find the dots. Dots are cool. That's a lot of cool information. But with this high angular resolution radio astronomy that interferometers allow, we can zoom in on these dots. So here are 9 different zoom ins where we can actually see the individual stars forming. We can see and observe star formation with ALMA and the VLA. The blue images are ALMA images, the red images are VLA images. These are operating at 2 different wavelengths, so they're giving complementary but different information about how these stars are forming. Absolutely astounding. Let's take a look at another really, really cool discovery, again with ALMA, our highest resolution interferometer in the world right now. This background image is from the Gemini Observatory. It's an infrared image. We're again looking at the Orion Molecular Cloud Complex, but now we're looking at the Orion Molecular Cloud 1. That was what we have in the background right here. So you can see some of the dust associated with this. You can see stars that are being born. Molecular clouds are where we see active star formation. And in this particular one, we can take an image with ALMA and we see this ring around this young hot star, a ring of material encircling this young hot star. And not only that, remember that radio waves are really looking at molecules. So we can tune the interferometer to look for certain spectral lines. We can use spectroscopy And this one, they used spectroscopy and they found spectral lines associated with two different molecules, sodium chloride and potassium chloride. Salt. Sodium chloride is your table salt. You probably use potassium chloride as well. You can eat it too. Salt. Here we are looking at a disk that contains a large amount of salt out there in the universe, in the Orion Molecular Cloud Complex, around a supermassive star, and the universe is naturally forming salt. Awesome. Okay. I think this is the last one. I thought about just continuing this forever, but the video must stop at some point. Here, we're going to focus in on high resolution radio astronomy so we can observe and study star formation on a galaxy-wide scale. So there's an entire survey going on that's looking at different spiral galaxies and looking at star formation in those spiral galaxies. So this is, again, an ALMA image, but now it's tuning itself to look for a spectral line related to carbon monoxide, which is what we use to trace out where all these molecular clouds are. And remember, molecular clouds here that we just learned are related, this is where stars form. So this is mapping out star formation by determining where all the molecular clouds are in all of these spiral galaxies. Each one of these bright regions is a molecular cloud where there's active star formation happening on, and active formation of different molecules as well. Each one of these blobs, the bright blobs, is maybe only 100 light years across, and these are galaxies that are millions of light years away, tens of millions of light years, hundreds of millions of light years away from the Earth. And here we can see molecular clouds that are only a few hundred light years in diameter. And we can study how star formation proceeds in spiral galaxies. And hey, we live in a spiral galaxy, the Milky Way. So I hope this video not only taught you a lot about the amazing world of radio astronomy, but also showed you how so much of what we've studied is coming together so we can really, really get fascinated by what we learn about the universe. Here we've used spectroscopy to define molecules. We've used radio astronomy to focus in on those molecules. We've used radio astronomy to see a part of the universe that we can't see in visible light. We've used visible light to add a lot of context to what we're seeing in this other part of the electromagnetic spectrum. What we have left to do is just to do this kind of work in all parts of the electromagnetic spectrum. That is the goal of astronomy, is to observe the universe in high detail, good angular resolution at all possible wavelengths in the electromagnetic spectrum. As a species, we're just now starting this process. We just are really starting to discover what's out there in the universe. We are in an age of absolutely huge discovery about things in our universe. All you have to do is build a new telescope, design a new interferometer that's sensitive in a different part of the electromagnetic spectrum where we haven't studied the universe. You're almost guaranteed to find surprising things out there and make foundational new discoveries about our universe. It's a great time to be alive as an astronomer. Thanks for tuning in.